An important aspect of public blockchains are fee markets. They protect the blockchain from so-called denial of service attacks, and they determine which transactions will get included first. And particularly from an economic point of view, it's super interesting to study the mechanisms that in many cases closely resemble auctions for priority access to the blockchain. And that is exactly what we're going to look at right now. All right, let's go. Now, in order to understand the mechanism behind transaction fees, we first have to look at the motivation, basically the reason for their existence. And we can best do that by looking at a paper that has been published in 1936 by Alan Turing. Basically what he says in that paper is that when you have a machine, so an execution environment, that allows for a relatively sophisticated instruction set where you have flow control, so things like loops and so on, the machine cannot tell whether the script will end at some point, whether it will converge to a solution, or if it will simply run forever. This is not something that the machines or the execution environment can evaluate. And this, of course, has severe implications in terms of security, especially when you think of public blockchains. And a potential attack vector of a public blockchain would be that when you have, let's say, an infinite loop in a smart contract, then the validating nodes, they would simply evaluate that one smart contract or the execution thereof forever. So an attack vector would be someone deploying a smart contract with an infinite loop, and then sending a transaction that executes that function, triggers the infinite loop, and then the validating nodes, they would just verify, and they would be basically stuck in that state. And if you do that a number of times, then you could essentially generate a denial of service attack where all of the verifying resources are bound in this process. So essentially they're just verifying the same process over and over again without realizing that they are in this state. Now, of course, you could say there could be a hard cap on the transaction evaluation. And with the validating nodes, you could say, okay, once we have reached a certain number of execution steps, we're simply going to stop. And this might be fine for most applications, but then again, you could have some applications, some smart contracts that are significantly more complex than others. So it would be really hard to set a hard cap like that and come up with a number where you're saying that's the number of computational steps we're going to allow. And also another thing is, I mean, how would you measure that? It would have to be in steps, so it would have to be in some unit that represents the computational resources. You couldn't use time, for example, because time that heavily depends on the hardware that is actually employed in the process of verifying, and this might be different for each and every verification node. So again, the essential problem is that you must have a solution that the verification either cannot reach an infinite state, so that it's impossible to generate these loops, or option B, you must have a solution how you deal with it when you end up with it. And these are essentially the two different solutions when we talk about Bitcoin and Ethereum. They both deal with these problems, but they do so in very different ways. With Bitcoin, as those of you who have taken the Bitcoin blockchain and crypto assets class already know, with Bitcoin you have a relatively limited scripting language, so Bitcoin script, where you just have some limited OP codes, no flow control, no loops, nothing that could bring the script in a state or just infinitely verifying things, and they deal with it in that way. So you have this deliberately limited scripting language that doesn't allow for things that could potentially be dangerous and bring the verification nodes in a state like that. With Ethereum, it's slightly different. With Ethereum, you have much more flexibility. With Ethereum, you have a Turing-complete instruction set, and therefore Ethereum has to deal with that problem in a different way. And the way Ethereum is dealing with it is by charging a transaction fee per computational step. So the idea is that whenever you're doing something within a transaction, then this will lead to a certain cost. And the cost depends on the number of execution steps, the number of computational steps you're taking in that transaction. So in other words, in very simple terms, the more complex the smart contract you're executing, the higher your transaction fees. Now, how is it done? I mean, what you're doing is every Ethereum virtual machine operation consumes a predefined amount of gas. And gas really is the unit of computational steps with Ethereum. So basically you're saying we must have some way of comparing these different computational operators, so these different OP codes, with each other, and we're doing this through units of gas. And then each of these OP codes has a pre-specified cost associated with it, cost in units of gas. And of course, you cannot change these parameters as a user. That's just something that's given by the protocol. This is basically the protocol saying when you want to add something, then you have certain costs involved. When you want to subtract something, then you have certain. When you want to multiply something, it's a certain cost. And these are really these units of gas. To give you some examples, an addition is 3 gas units, multiplication is 5 gas units, and if you want to store something, in this case 256 bits on the blockchain, this is 20,000 gas units. So these are the costs associated with these OP codes. Now, as a user, as I said, you cannot change these parameters up here. So you cannot change the cost of these OP codes, but there are 2 parameters you can change. And maybe before I get started, I have to also mention that what you're about to see right now is the original system, as it has been implemented with Ethereum originally, and that has been in use for several years. After I've shown you this system, we will also talk about EIP 1559, which is in effect since August 2021. But that's something we'll turn to later on. Now, as I have said, you cannot change these values up here as a user. So this is just something that's given by the protocol. But there are 2 parameters you can change, and something you're passing alongside every single transaction. And that's the first one is called gas limit. And gas limit essentially specifies how many units of gas you're willing to pay max. So essentially you're saying as a user, I'm willing to support this transaction for up to X amount of gas units, so X amount of computational steps. And if there is no conclusion reached with this number of execution steps, with this number of gas units, I'm just going to abandon the transaction, then it will fail. So this is really the maximum number of computational steps you're willing to pay for. That's called gas limit. And to give you some example, with a simple ETH transaction, it's 21,000 that is required. And of course, with the contract execution, this varies with contract execution. This heavily depends on the complexity of the smart contract. And the second thing you're also choosing as a user when you're issuing a transaction is called gas price. And this is essentially where the auction happens. This is where you're saying, I'm willing to pay X amount for each gas unit that will get consumed in the process of the transaction. Okay, so here with the gas limit, you're specifying how many computational steps the transaction can take. So that's the cap, the maximum number of computational steps the transaction can take. And this, the gas price, is you saying that's the max, that's what I'm willing to pay per computational step. That's the price I'm willing to pay for each unit of gas. Now, of course, miners, so the people who are confirming a transaction, they are incentivized by this. There is in each block, so when they assemble the transactions, there is a block gas limit. So basically, which basically determines how many, not how many transactions, that would be wrong, but how much computational resources can be part of a block. And this is split among any number of transactions, depending on the gas limit or the gas used of each of these transactions. But what miners really care about is your gas price, because that is you saying, I'm willing to pay amount X for one computational unit. And that essentially is what you're willing to pay in relation to the space it takes in the block. So that's the fee you're paying to the miners. That's your auction mechanism for priority access. Now, the way these transaction fees work is initially what you're doing is you're placing an amount in Quay equal to gas limit times gas price in transaction escrow. So you're saying, okay, if this transaction gets confirmed, I'm willing to take number of computational steps that corresponds to my gas limit, and I'm willing to pay gas price per computational steps, and that's why you have gas limit times gas price. That's the maximum transaction fee you're paying in case all of the gas limit will be used. And we're saying it's transaction escrow, so it's transaction escrow because essentially your transaction, you can think of it as your transaction carries this fee, and whenever it gets confirmed, then the miner can take up to this amount. So initially you have the transaction initiation right here. You have something called remaining gas, and this initially will be set to the gas limit. So when you start out with the transaction, when the transaction initially gets executed, then you have remaining gas equal to gas limit. What happens then is, you're reaching here the question if remaining gas is 0 or if it is insufficient to execute the next OP code. In most cases this will be a no. In most cases it will neither be 0 and it will also not be insufficient for the next OP code. And what you do then is simply execute the next operation, so basically the next instruction within the transaction that is part of the transaction, that is executed as part of the transaction. And then what happens is the new remaining gas right here becomes the previous remaining gas minus the OP cost, okay? And this makes sense. Since you have executed an operation, the cost of this operation will simply be deducted from your remaining gas. Then you're reaching here the question, are there any remaining operations? Or is there anything else that is part of transaction execution? If the answer is yes, you're going back. You do again the remaining gas 0 or insufficient check. Let's say that's not the case again. Then you have the next execution. The next operation will be executed. Again, remaining gas will be set to remaining gas minus OP cost. So in other words, the OP cost of that operation right here will be deducted. And then you're asking, are there any remaining operations? Now, we assume again that there are remaining operations. And in this case right here, let us just go with the example that we're saying the remaining gas is either 0 or it's insufficient to execute the next operation code. In that case, the transaction will simply be reverted. And reverted in this case means that the transaction does not lead to any state changes except the update of the nonce from the initiating party, so from the initiating externally owned account. The nonce will be updated. Also, the transaction will be part of the blockchain, so everyone can see that there is a transaction, but it will be in a failed state, and none of the basically the idea you had, none of that will be executed. So it will be reverted, and any other state changes will not be applied. It will simply just be the nonce that gets updated, but anything else you wanted to do will not be applied. But again, the transaction still is part of the blockchain, but just in a state where it's clear to everyone that it did not lead to any changes. Now let us go back right here and say there is enough gas for the next execution. So then we have a new operation that gets executed. The remaining gas will again be adjusted. The OP cost will be deducted. And then you have again the question, are there any remaining operations? And at some point there aren't any remaining operations. At some point you're seeing that the transaction halts. And in this case, you can say the transaction is successful. Now, successful means that everything the transaction wanted to do will be applied in accordance with the smart contract. So basically you can see some state changes in addition to just the nonce. It simply gets executed. And number two is that you get back a refund, which corresponds to the remaining gas times the gas price. So whatever has not been used as part of the transaction, so when there is a positive remaining gas, then you will get that back as a refund. It will not be deducted when your transaction is confirmed. So that's the idea, that's the structure. Now let me give you an example with some numbers. Let's say you have this person right here, and this person initiates a transaction, sets the gas limit to 100 and the gas price to X. Then when the transaction gets executed initially, the remaining gas is of course 100, right? We haven't applied any OP codes yet, so it's the same as the gas limit, it's simply 100. And that's the case here at the start, okay? At the start, the remaining gas is 100. Now let's say we have an addition as part of the transaction. This would be -3, so the remaining gas during the transaction execution in this case is at 97. Then the next step is a multiplication. So the remaining gas would be at 92. Okay, because we have here -5. And then let's say we want to compute SHA-3 hash value. It's -30, so it would be 62, the remaining gas. Now let us assume for this super simplified example that these are all the operations that are part of this transaction, part of the execution. So at the end of the transaction, you still have a remaining gas of 62. What does it mean? Well, what it means is the user, so that's the same person right here as this one, that's just one user you're seeing, the user gets back 62 times X quay. X being the gas price he initially set, and 62, that's just the remaining gas. That's what he didn't use. Okay, so basically that's the refund, and that's the idea. That's how these transaction fees work. And again, gas limit simply sets the number of steps you're willing to take. Gas price is the auction part of it, so that's what you're willing to pay for one step. When you're taking one step, that's what you're willing to pay for that step. So namely for a unit of gas. Now on August 5th, 2021, this changed. When we had this proposal, this Ethereum improvement proposal, or EIP, with the number 1559. And this completely changed the entire transaction fee mechanism on the Ethereum blockchain. It was implemented through the London hard fork, so there was essentially a hard fork at a number of changes, but mainly this change of the transaction fee mechanism. Now, issues that have been addressed by this proposal were the following. Number one, there has been a certain mismatch between the volatility of transaction fee levels and the social cost of adding an additional transaction. What did they mean by that? When you look at the transaction fees, they have been quite volatile. It's been extremely unpredictable before EIP 1559, and the blocks have been full, so at their maximum capacity in almost all cases. And the reasoning here is that one more transaction is not that much of a burden to the blockchain, so there should be some more flexibility. It's not that much of a social cost when you have an additional transaction, whereas when you have this immense volatility with the transaction fees, this unpredictability and this uncertainty, this might be a huge cost. So with EIP 1559, and we will see later on how exactly it got implemented, with EIP 1559, the idea was to essentially make transaction fees a little more predictable and also allow for some different sizes of blocks. There is a target size, as you will see later on, but when there is a huge demand, then it can expand a little bit, and when there is less demand, then it gets a little smaller, as you will see. Number two is that we have seen many delays for users. This again also has to do with this hard cap of the block size limit. That isn't necessary to have a system where you, even if you have a relatively large transaction fees or a relatively high gas price, you simply have to wait because you have this single hard cap and cannot really do anything about that. So EIP 1559 also tries to solve that. And then, of course, you have inefficiencies of first price auctions. That's a topic that has been in economics for a really long time. To give you an example, when you're setting a gas price, you have to know exactly what other people are willing to pay. Otherwise, you are at a severe risk of overpaying, right? I mean, when you have no Oracle access, when you have no data on what other people are paying, or when you don't have access to the current mempool yourself, so you're observing the other transactions, then you're really in the dark. You don't know exactly what you're doing. You don't know what you have to do. And then you are at a severe risk that you're just picking some gas price, which may be either way too low, and in that case, your transaction will not be included, or it may be much too high, maybe a gas price that is significantly higher than anything else. In that case, you're simply overpaying. The miners can take the entire transaction fee. They're taking everything you set as gas price, even if it's much too high, even if it is significantly higher than what you would actually have needed to get into the block. So EIP 1559 also addresses this issue. It's not the first price auction anymore. It's something that is closer to a second price auction, although that's not entirely correct to state. But it's something that closely resembles a second price auction and has many advantages in terms of the economic properties. And then, of course, you have the instabilities of blockchains with no block rewards, where you could have certain transactions with a very high fee. And in the absence of a block subsidy, so when you have no block reward, this could lead to major issues. This could be a problem where, for example, I see that somebody else has confirmed the transaction with a very high transaction fee, and I'm not happy about that this transaction is not part of the mempool anymore because I wanted to confirm it as part of one of my blocks. And this gives you some incentives for things like selfish mining, reorgs, competing, deliberately competing instances of the blockchain. It's just not a good state to be in. And with EIP 1559, this also gets at least partially addressed. Key changes: number one, you have a dynamic base fee, which gets which is endogenous to the protocol. So it basically gets computed as part of the protocol. It gets set as part of the protocol. And what is also new, this base fee will not be distributed to miners, will not be distributed to the people who confirm the transactions, but instead will be burnt. So it will be destroyed, okay? And then, as you will see later on, there's a tip on top of that, and a tip, or also called priority fee. That's the idea that basically you can incentivize the miners to include your transaction, but we will look into that in greater detail. And number two, variable block size. There still is a hard cap at some point, but this hard cap is significantly higher, and the target value for the block is actually 50% of that hard cap. And as you will see, when you're above that target value, so when blocks when there are more transactions in the blocks, when they are fuller in terms of gas being used in the block than 50% of that max cap, so when it's higher than the target value, then the base fee will be increased, and otherwise it will be decreased. So essentially the system tries to incentivize people to always go back to that target value by adjusting the base fees, or by adjusting one part of the transaction fees. Now, let's quickly look at an example of a transaction before EIP 1559. So again, we go back to the original model, the one we've discussed before. And here you can see a first price auction. The user specifies a gas price he or she is willing to take, he or she is willing to pay for the transaction, okay? And the user does that by specifying right here the gas price. And this gas price simply gets paid to the miner. So gas price times gas used, that's the compensation that the miners get, as you can see right here. And it's really the entirety of the transaction fee goes to the miner. Now with EIP 1559, that's a little different. With EIP 1559, the network sets this base fee, and the base fee, as you will see later on, depends on the demand for block space in the previous blocks. And this base fee can be adjusted by a maximum of plus or minus 12.5% per block. So it goes up and down depending on the demand. We will look into the equation, how this is exactly set later on. But depending on the demand, when there is a lot of demand, when blocks are full, then it will be increased by 12.5% per block. When they're completely empty, then it will be decreased, the base fee. And in addition to this base fee, there is a priority fee, as I said, and this priority fee is set by the user. So it's not set by the protocol as here the base fee. This is something that can be chosen by the person who initiates the transaction. And as I have already stated, that's essentially the tip you're paying to the miner. And then you're also saying, you're also specifying a max fee. And the max fee, that's what you're basically what your represents your maximum willingness to pay for the transaction. The reason why this exists is because, as I said, this part, so the base fee, is determined by the protocol. It's endogenously determined by the protocol. So the base fee could increase, and just to make sure that your transaction still could get through when the base fee gets increased, so when there's a really high demand, you're also specifying this max fee. And this max fee is something that incorporates base fee, priority fee, and then usually you have some slack right here just to make sure. Now the base fee again gets burned. That's something that will be destroyed. The priority fee is something that compensates the miners. So that's basically your tip to the miners. That's something you're giving them. And if that's the case, then you also get a refund right here. You're not paying up to your maximum amount, and that's a big difference. That's why I said it's not really a first price auction, because the miners, they cannot simply take the difference up to your max fee. They are really limited to whatever you're setting as the maximum priority fee right here. And in this case, this would be your refund that will go back to you. So let me actually revisit the terminology really quick. We have the base fee right here. The base fee is calculated by the network. It's endogenously determined as part of the protocol, and it depends on the demand for block space. As I said, it can increase or decrease by a maximum of 12.5% from one block to the next one. So it decreases by 12.5% if the demand for block space is at 0, so when there are no transactions in the block, and it increases by 12.5% if it's twice the target rate, the current block size target, so the maximum block size, then it will increase by 12.5%. And as I also have stated, it gets burned by the network. It takes ETH out of circulation. That's the idea. That's also how it addresses the issue where there might be no reward and all of the problems that are involved with that when you have no block subsidy. Because when you're taking out ETH of circulation, then it might also be more reasonable to introduce a block subsidy, a block reward, without having any implications on the current number of ETH that are in circulation. That's something that could potentially be super interesting later on. And then you have the priority fee, the tip. It is set by the user to give the miner an incentive to include a transaction in the block. Of course, miners receive that incentive, otherwise it would not be an incentive. But the big difference is that it's just part of the transaction fee, which actually goes to the miner with EIP 1559. And then you have the max fee. The max fee corresponds to the maximum willingness to pay for 1 unit of gas. And the transaction, as we will see, remains pending if the base fee is greater than the max fee. In that case, it will remain pending. In that case, there is no way it can get included to the blockchain until the base fee drops down. Then, of course, the transaction could get included again. And you have a refund. The refund really is the maximum of 0 and the max fee minus base fee plus max priority fee. So if you don't, that's basically the example we have seen right here. Here we had a refund, right? If you actually go back, and that's because the base fee plus the priority fee was smaller than the max fee. That's exactly what we're seeing here. Now let me show you that in a graph really quick. You have on the x-axis the base fee right here, which is also reflected here on that line. That's also the base fee. And on the y-axis you have ETH divided by computational steps. So that's just some measure of ether or denomination thereof for each computational step. Then we also have the max fee right here. That's the maximum you're setting that you're willing to pay with the transaction. And the max priority fee, that's the maximum number, the maximum amount you're willing to tip the miner. And you can see, of course, the max priority fee is this amount right here. If there would be a base fee of 0, then this would be all you pay. And of course, when the base fee is increased, then you always add the max priority fee on top of it. And that's your total cost, okay? And everything is fine until you're right here. And right here, you have actually a special case, because right here, what miners could choose to do is they could optionally decrease their own tip and say, okay, I'm still going to include that transaction, but since the user has specified that this is the maximum he or she is willing to pay, this of course will lower the tip value for the miner, because the base fee to the protocol always has to be paid. And then starting right here, we have a third case, starting right here, when the base fee is larger than the maximum fee, then it will simply not be included. I can actually show you that really quick. I mean, here we have the first case. I've talked about the refund case, which is super easy. If the base fee plus the maximum priority fee is smaller than the max fee, then there will be some refund, and that's the case right here. We have the base fee right here, this part. We have the tip right here, so the priority fee, this part. And then starting from here to here, that is the refund, as you can see. And here you also have it on the slides. And this is for the base fee low, as specified right here. We have in red the burn low, we have in green the tip low, and then we have the refund low. And of course, burn will be burned, tip goes to the miner, refund will go back to the user who has initiated the transaction. In case 2, we have a little higher base fee, so a base fee that is in between right here and right here. And what's special about that, as I said, is the tip will be decreased. So the miners, they choose deliberately to decrease their tip in order to being able to still include the transaction, in order to being able to have a sufficient base fee that will be accepted by the protocol for this transaction. And that's the case when the base fee plus the maximum priority fee is larger or equal to the max fee and the base fee lower or equal to the max fee. Okay, so that's really this sweet spot right here. And again, when we look at what happens right here is the red part here, burn mid will be burned. Tip mid, that's a little smaller tip right here. So that goes to the miner. That's the incentives for the miner. In this case, he or she has been willing to accept that. And of course, there is no refund because the miner will simply take whatever he or she can take up to the max fee. It's not higher than the maximum priority fee. In that case, he or she can take everything. And of course, then there is no refund. And the last case is actually the easiest one. I mean, in this case, as I said, when the base fee is larger than the max fee, then it will be a pending transaction until the base fee gets lower and the max fee. There is no burn, there is no tip, there is no refund, simply for the reason because this transaction will not get confirmed in that state. It cannot get confirmed in that state because the base fee exceeds the maximum fee set by the user. Okay? This really, you can think of it a little bit as an exclusion zone. It's impossible. It cannot get included. It cannot get confirmed as long as this condition, so base fee larger than max fee, holds. Now let's look at how the EIP 1559 base fee is actually adjusted. I've given you the intuition how this works and said when blocks are full, meaning that the gas used is higher than the target value, then the base fee will increase, whereas if the gas used is below the target value, so if you have fewer transactions in the blocks, then the base fee will decrease. But let's look at that mathematically really quick. So there is something called target block size, and that's currently 15 million gas. So that's the target, that's something we actually want to have, that's something that has been set, and that's 15 million, and we refer to that as S target. And then you have the block limit. So that's the maximum cap. It cannot get any higher than that, and that's around 30 million gas right now. It varies slightly, but essentially what it is, it's twice the target block size, okay? So 15 million, that's what you want to have. 30 million, that's what you could have. That's the cap, the maximum. And now the block size and the base fee of the previous block, so the S of the predecessor, so basically what has been used in the predecessor, and the R of the predecessor, so that's essentially the base fee of the predecessor, they determine the base fee of the current block, so R current, okay? And we can see that right here. We define R current, so the base fee of the current block, as R predecessor times 1 plus 1/8 times S of the predecessor minus the target S divided by the target S. So that's the target value right here. These are the S target, these are the 15 million, and the S predecessor is what has been used in the previous block. So let us actually go with an example. Let's say that the gas that has been used in the previous block is 0. What happens? Then we would have S predecessor would be 0 minus 15 million divided by 15 million. Of course, 0 minus 15 million is minus 15 million. And then if you divide that by 15 million, you would end up with a negative 1. So what we have right here would have the previous base fee times 1 plus 1/8, and these are these 12.5% that I've told you about earlier, and then minus 1. So it would be 1 minus 12.5% essentially, and that's how you end up with that. So when you have a completely empty block, then these 12.5% will get deducted for the next base fee. Now the maximum you can have is these 30 million, so twice the target value. When you have twice the target value, you would have S predecessor 30 million. S target would still be 15 million divided by 15 million right here. And of course, what you would end up with up here would be 15 million. Why? 30 million minus 15 million is 15 million. You divide it by 15 million, so it would be 1, because it would be 15 million divided by 15 million. In this part of the equation, you would have 1 plus 1/8 times 1. So essentially 1 plus 1/8, and of course this would again be the 12.5% increase that we have seen. And that's why you have this range. That's why it can be decreased by a maximum of 12.5% if there is 0 demand for block space. But it can also be increased by a maximum of 12.5% if the block is completely full. If every single gas unit is being used, then it will be the increase of 12.5%. Now, if you want some information on current gas prices, and this is not that important anymore with EIP 1559, because again, it's not the first price auction anymore, but still it's a good idea to have some understanding on the current base fee, so that you know how you set the maximum fee. And also it's good to have some understanding of what priority fees or tips you have to set to get a transaction through. And there are many resources. 2 of the more prominent ones are Etherscan. They have some information on current gas prices, but also Eve Gas Station. And these are some resources you should look at. And also, of course, it's always helpful to look at the previous blocks. It's also helpful if you run a full node to look at the mempool to get an understanding of the current gas prices. Now let us wrap up with the exercises. And in this exercise set, you will play around with some different parameters for transaction fees. You have exercise A to E. But for every single one of them, you have two assumptions. Assumption one is that the base fee corresponds to this value right here, so 0.00 and so on, 13 Gwei. That's obviously a value that's only realistic for Ropsten testnet, not for Ethereum mainnet. On Ethereum mainnet, that would be really unlikely. But since you are expected to also try out these transactions, and we expect you to do this on a testnet, we chose the parameters in a way that it makes sense for the testnet later on. And then, of course, threshold priority fee, so where we say that's what the miners accept. That's the minimum you have to give them until that they accept it, of 1 Gwei. Okay, these are just the two assumptions. Now, with these two assumptions in mind, when in exercise A, we set the max priority fee to 2 Gwei and the max fee to 3 Gwei and the gas limit to 21,000. Okay. And what's important also is that we are initiating a simple ETH value transaction. So it's not some smart contract call. It's really just an ETH value transaction. For exercise B, we use a max priority fee of 0.5 Gwei, a max fee of 1 Gwei, and a gas limit again of 21,000. For C, you have the max priority fee of 2 Gwei, a max fee of 3 Gwei, and the gas limit of 1 million. Is it 1 million? Let me check. 1, 2, 3, 1, 2. Yeah, that looks like 1 million. Great. And then with D, you have a max priority fee of 2 Gwei and a max fee of 3 Gwei, a gas limit of 1,000. And with exercise E, it's a max priority fee of 3 Gwei, a max fee of 3 Gwei, and the gas limit of 21,000. And the way you should approach these exercises is first by looking at them and try to come up with an intuition. With these assumptions you have up here, these two assumptions you have that count for every single one of these exercises, and then the specific parameters in each and every one of these exercises, you should come to a conclusion, have an idea of what actually happens. If the transaction will actually get through, if it will fail, if it will lead to state changes and so on, and also some estimate of how long it will take. Okay, that's the idea. And then once you have done that, once you have a intuitive understanding of it, and you're pretty sure that the conclusion you reached is correct, you should try it. Try it on Ropsten testnet. You know how to do that now. We set everything you need up last time in one of the last videos, and then just try it out and see what happens. And that's the idea of these exercises. So the first thing we have to do is adjust some settings. Click on the icon up here, then go to settings right there and on advanced. And on advanced, you have different settings we're going to change. The first one being the advanced gas controls. You turn that on. This allows you to adjust the gas parameters. Then the next thing is to show hex data. You will need that later on for smart contracts. And one more thing, that's customized transaction nonce. You will also need that for this exercise to manually adjust your transaction nonce. Now, with that, let's start with the first transaction. So with exercise 1A, we are going to send some ETH to the second account, so from the first to the second, 0.01. And then what you're doing is you go on edit right here. That's where you have the advanced gas options. You change the maximum priority fee to 2 Gwei, and you change the max fee to 3 Gwei as stated in the exercise. And then you save that and confirm the transaction initiation. Now let us quickly check on Etherscan. And on Etherscan you can see that the transaction is pending, and as always this is going to take a while, and we speed up things a little bit. So we're going to go with a 2x speed, and then after a while, and there it is, we have the confirmation. Okay, so you can see it's a success, it's confirmed, the parameters you have set are sufficient. With that, let's go to the second exercise, so 1B. And for 1B, we again pick the second account as a destination. We again transfer 0.01 ETH. And then we will click on edit again, but this time we adjust the parameters in a different way. So what we're doing is we set the max priority fee to 0.5, below the minor threshold value, and the max fee, we set that at 1 Gwei. Again, it already warns us, so we can see that there might be something going wrong, but let's try anyways. We confirm the transaction initiation, and again, as always, we're going to Etherscan to check the transaction. Now, spoiler warning, the transaction will not get confirmed because the priority fee is below the minor threshold value. I wanted to see that and show you that it doesn't get confirmed, even if we wait for a really long time. But of course, I don't want you to have actually waiting for it. So I decided to go with a 20x operator to speed up the video. And now we have waited for almost 10 minutes. So let's try something else. It's not going to confirm, and that's also clear from the intuition. But you can see here the transaction has nonce 2. So that's important if we want to issue a conflicting one. MetaMask actually has 2 buttons. One is cancel, one is speed up. This is just really helpful because behind the scenes what it does, it also plays around with the nonce. It uses the same nonce, but we're going to do that manually. So we're going to send the transaction to ourselves, a 0 ETH transaction to our own account. So we picked account 1. And this time we're going to use some parameters that will actually get through. So we use max priority fee of 2 and the max fee of 3. We readjust the nonce to 2, and that's super important. We don't just go with the one that's been set by MetaMask. We go back in order to make it conflicting with the other transaction, and then we check it out. It also takes a while, of course, but it will get confirmed eventually. And that just happened right now. As you can see right here, success. You can check the nonce once again. It has nonce 2, so the same one as the previous one. And if we check the other one, then we realize that the original one has been dropped. The Explorer cannot even find it anymore. It has been dropped. It cannot get confirmed because the conflicting one with the same nonce has been confirmed. Let's go to exercise C. Once again, we pick account 2 as a destination. Once again, we send 0.01 ETH. Click on next. And we adjust the gas parameters. So what we're doing with exercise C is we're going to adjust the maximum priority fee to 2, the max fee to 3, but more importantly, we're going to adjust the gas limit to 1 million in this case, okay? And remember, these are the execution steps you're willing to take. That's not what you're paying per execution step. The gas limit is just how many execution steps you're supporting. Again, going back to Etherscan, waiting for the confirmation. We already have it. And now what's interesting when you're scrolling down, click on see more, you can see right here that although you have set the gas limit to 1 million, only 2.1%, so again, these 21,000 have been used and the rest has been given back to you as a refund, so you're not paying that. So when you're setting a really high gas limit, it doesn't necessarily get consumed if not necessary. Let's go with the next exercise, with exercise D. Again, 0.01 ETH to account 2. Again, we are setting the parameters with edit. And this time what we're doing is we're setting the gas limit to 1,000, max priority fee to 2, and the max fee to 3. You can already see we cannot even confirm the initiation. It says it must be at least 21,000. If you would do that, it would fail. MetaMask prevents you from doing so. If you would use an example with smart contracts, you could actually bring it in a state where the gas limit is too low, and then you would see that the transaction fails. But here we're going to reject it. We're going to actually close it and proceed with our last exercise with exercise 1E. And with 1E, again, we choose the second account as a destination. Again, we go with 0.01 ETH. Again, we're going to adjust the parameters with edit. And this time we choose a max priority fee of 3 and a max fee of 3. We don't change anything else. And what's interesting, when both of these are the same, then you will see once it gets confirmed, and we already have the confirmation, that the tip that the base fee will be deducted from the tip, so from the priority fee. You can see that right here. We have the base fee that got paid, and we see that something got burned. So the miners have been willing to lower their tip in order to be able to pay for the base fee and get the transaction included. Alright, so that's it from the transaction fee video. I have two recommendations in terms of reading. Number one is the transaction fee mechanism design for the Ethereum blockchain by Tim Roughgarden, where he analyzes EIP 1559 from a game theoretical perspective. So particularly to those of you who have an economics background, and I assume that's the majority, this might be extremely helpful to get a deeper understanding of EIP 1559. And the second thing is, if you have any remaining questions, of course, there are many different resources, but one of the best ones I think is the FAQ by Vitalik, where you basically have the most frequent questions regarding EIP 1559 and of course the answers to it. And with that, stay curious, see you soon.